Minute left, but I think we can just slowly transition here to Faeze Aminmansoor. So Faeze is, like myself actually, an engineer and physicist by training. So welcome to the club here. Lots of neuroscientists, in particular computational neuroscientists, have exactly your background. Like Konrad Curting, for example, is the same. And of course, now she's working in neuroscience and actually looking for a PhD position. So if anyone is out there that particularly like her talk or her presentation, maybe this is a good time to get in touch with her. So in general, Faeze is interested in questions about human and mental and cognitive capabilities and also development of intelligence. And today she will be talking about the collective response of oscillating neural population to an applied perturbation. And that is based on a computational framework. All yours, Faeze. You have to unmute yourself.
Okay, thank you for the kind introduction. So the question that we were interested in answering is basically related to understanding better the communication between cortical areas. So we know that all the fabulous cognitive behavior that our brain is capable of doing is based on some communication and some signal exchange. A common phenomenon between all of this is that how a network would answer to an incoming input. To approach this question, we take into account the oscillatory behavior of the cortex, which have been seen in different scale, like LFP, EEG. The spikes are coupled to certain phase of LFP oscillation. And we frame our question as follows: what will happen to the activity of the network if an incoming perturbation arrives at different phase of an oscillation? So for that, we used a well-known framework in physics, which is the phase response curve. A brief explanation about that is that if you take into account any physical oscillation with period of T0, if you apply a brief perturbation to the oscillator, the subsequent cycle of the oscillator might get advanced in its timing of happening, or get a delay, or remain unchanged. So this change in the shift is normalized by T0 and is defined a quantity called resetting. And when we plot the resetting with respect to the phase of the incoming perturbation, we will get a graph called phase response curve, which is a characteristic feature of the oscillator. So based on this, people define two types of neurons. Type 1, like intermittent fire neurons, are always experiencing and advancing their activity. And type 2 neurons, like Hodgkin-Huxley, are experiencing both delay and advance, depend on the timing of the arriving input. So we used a network. So we use a network of LAF neurons, and you can see that LAF neurons are always positive in their phase response curve. So we used a network of LAF neurons, a recurrent network, which are connected randomly, and the connections were sparse or relatively sparse. So 500 neurons were taken. The synapses were current-based, and they were modeled using delay difference of 2 exponentials. Then we applied an infinitesimal pulse to the network. And by infinitesimal, I mean the duration of the perturbation is 0.5 millisecond, and the amplitude was from the order of 1 millivolt. And we applied that to just 10% of neurons. And so we want to see what the collective response curve of all of the population of neurons would be. So before showing you the results, I would like to give you some intuition about the dynamic of the network. Here in the top graph, you will see the scatter plot of 500 neurons. In the middle graph, you are seeing spike density function. So the vertical axis is firing rate of the network. And the bottom graph is the LFB of the network, and the horizontal axis is time. So I will apply perturbation on different phase of oscillation between these two peaks, and let's see how the network is changing its activity. So first of all, I would like you to pay attention to the subsequent the time ahead of itself. Here you're seeing like 100 milliseconds ahead of that small perturbation, and you can see that different pattern of activity would arise. Sometimes there's more tendency to discharge in a synchronous pattern, sometimes less synchronous, and in fact, they have tendency to discharge asynchronous. So and I'm showing you just like 100 milliseconds ahead. This duration is longer actually. Then I would like you to see this change in the amplitude of the subsequent oscillation, as well as its the phase shift, delay or advance. Then take into account that bump, which is moving with respect to the perturbation, and the whole manipulation of the LFP can be seen in the future of the network. So I think that's pretty cool. And let's see what's the result of collective phase response curve of the network. I take 30 trajectories coming from an ensemble of 5 networks, and this is the average value and standard deviation. So you can see that in the period of 2, in the complete period, the collective phase response curve is experiencing a delay at the early phase if the perturbation is applying at the early phase, and an advance if the perturbation is applying at the late phase of the oscillation. Also, in the amplitude response curve, you can see that initially the amplitude of the next oscillation is getting a decrease, and then followed by an increase, and again followed by a decrease for the second time. So why is this the mechanism? Why is this happening? So consider that a population of inhibitory networks work like this. A random set of neurons are discharging simultaneously, and then the discharge of these neurons induce an inhibitory signal to the old network. This takes time until the overall activity of the network get back to its resting state, and then in the second window of activity, another random set of networks are getting discharged. When you apply perturbation here, for example, the number of neurons which are getting discharged are getting enhanced. And this means that the overall inhibition of the network is increasing, leading to the network requiring longer time to getting back to its next oscillation. Which is equivalent to creation of a delay in the occurrence of the next oscillation. At the same time, because the discharge is taking place in a shorter period of time, the network has a tendency to be to discharge more synchronously. And that is why the activity of this next oscillation is getting enhanced. So then if we take into account a perturbation in this spot, here still the perturbation leads to an increase in the inhibition of the network, which leads to a negative value for PRC. And but because it is applied in the middle of the period, the overall network is experiencing smaller synchrony, and that is why the amplitude of the next oscillation is enhancing. And finally, in the C, if the perturbation is applied in the C phase, here this is the time window where the network is in its maximum excitability. So if the perturbation is arriving here, all the neurons which were supposed to discharge here are getting advanced in their discharging, and so the PRC has a positive value, and amplitude also getting enhanced because of that perturbation and the small time window that the perturbation is applied. So what I showed you is that timing of variable input matters. It affects on the future pattern of the network discharging regime. It affects also transiently on the frequency of the network because of the delay or an advance in it in the subsequent cycle of oscillation. And in the synchrony of the discharge of the subsequent cycle of the network activity. Also, I showed you the collective PRC of the population is independent of the PRC with single neuron. We talked in detail about the pattern of the collective PRC and amplitude and collective amplitude response curve. And a falsifiable prediction of this model is that if I apply a perturbation at early phases of SFT oscillation, which has an equivalent for LFP oscillation, this gives rise to transient reduction of network frequency, while applying in the late period of oscillation induce a transient increment in it. So I would like to thank my collaborator, Dr. Alireza Valizadeh, who was my first mentor in neural stimulation, and thank you everyone for attending. And I'm happy to take questions.
Great, thank you so much, Faeze. We have a question from Mohammed. Did you measure any complexity index, such as Temple-Ziff or entropy measures of LFP modeling in response to perturbations in different phases?
No, actually, we didn't do that, but I think it's a good idea. I think we should do that too.
I have some, while other questions are coming in, I have some very basic questions. So first of all, how did you ensure that you get your network to oscillate?
So this network that I described for you here is a well-known network mainly introduced by Bruno in 2000 and a couple of more papers are on it in 2003. These networks are, the dynamic of this network is what I explained to you, and that is a random number of neurons are getting discharged, and they induce that inhibition to all the network. The overall current of the network reduced, so no one can discharge. There's a silent period, then there is an enhance again, another random subset of network getting active. So this is
cool.
The way that this network is working.
We have another question from Joao. Great talk. Do you have any prediction on how different perturbations in excitatory inputs at different phases would affect different dynamical systems like Wilson-Cowan or coupled Wilson-Cowan models?
I was thinking actually on considering those models too, but so far, no, I have no idea how it might work on those models.
So one of the things I found really interesting is the fact that obviously the brain is known to oscillate, but we have very little knowledge about how these the relatively low frequency compared to the spiking oscillations affect the spiking behavior of neurons, right? Can you maybe say something about how this relates to spiking?
So I'm not sure if I get your question completely. These oscillations that it shows you are in the range of gamma.
So typically, like a lot of oscillations in the brain are much more low frequency, right? So we would have like 10 hertz, 20 hertz, so alpha and beta band oscillations that are believed to carry like sensory and motor signals, or at least correlate with them. Can you maybe say something about how these oscillations, based on your results, might influence the way that the brain processes?
I had another simulation, which was a study on those low oscillations when there are still that high oscillations exist in the network. And actually, I was working on the coupling, phase response coupling of the low and high oscillation. So what I learned from that study was that the slow oscillations are results of synaptic activity. In other words, there are if you measure the synapses, this in the model, if you measure the, for example, current of each synapses, you will get a very big power of low oscillation on them. But most of them are disappeared due to collective activity of neurons because they have different phase of activities. But at the end of the day, a small low oscillation would remain, and actually those small oscillation had phase amplitude coupling with the phase amplitude of the high frequency. So what I know is that, these are the effects of synaptic activity.
Great, thank you so much. We have to stop here. Mohammed asked whether the